the high energy intensive industries in Scotland, at least. And given that and the local location, it's very challenging to use low carbon fuels and low carbon electricity. It's about 10% of Scotland's final energy consumption. So just to get an idea of how much actually we could reduce the carbon footprint of this industry or similar industries, I created a model to look at supplying the main component of distillery, which is the wash still, by renewable energy, especially local renewable energy, because in Scotland the infrastructure, the grid is fairly weak, so we cannot assume that we can import and export large amounts of renewable energy across the country. Let's continue with that. I sort of put it in the Scottish context now. So we've got an excellent wind resource, a much lower but reliable solar resource. So solar thermal would never be sufficient to raise the temperature required. We need something around 100 degrees centigrade. And in this approach, we now use photovoltaics and wind electricity for electric heating. So rather than using solar heating through concentration directly, then we use electricity. But because the thermal storage is much more efficient in terms of round-trip efficiencies and self-discharge, we split the demand of the installation into a thermal storage for running the distillation process and a normal battery for the other electrical requirements of the site. And then we charge both storage devices from surplus generation and additionally use spare storage capacity to recharge overnight with cheap electricity as sort of just a way of also offering flexibility to the grid for more remote renewable sources. Right. Fundamental approaches, we've got a distillery, we've got resource and generation data, and we've got financial data. Everything still requires the bottom line. So this information, we know how much a distillation process needs. So from that, I created for this presentation a simplified synthetic demand profile. The location and also grid access. Can we import, export a certain amount of power at any time, and also tariff options. Then from the location, we know the wind speed and the radiance data from national local databases. I use the ERA 5 satellite data as an hourly resolution, and then selected sensible devices and combined those with device costs and electricity purchase and export tariffs. And then also, what is it do I want to do? So by finding the best solution, I need to define an objective function, what quantifies the performance and what is best. Do I want to save money? Do I want to improve self-sufficiency? Or do I want to maximize the carbon footprint reduction? So depending on what we want to do, all of this can be done in a sort of conceptual model of balancing supply and demand. So on the top left, we've got the demand of the system here, and on the right we've got wind speed and irradiation data. So in principle, we can turn the wind speed through a turbine selection into wind power, irradiation through a panel selection into PV power. Single unit power outputs, so how many turbines, how many PV panels do we need? There's NW and NP, and then how many storage devices do we need, and what is sort of our link to the grid with a certain limit. Right. We add the wind and PV power, balance it against the demand, and then get something called a residual demand. Red above the line means we still have good demand, so not enough renewable energy blue below the zero means you've got more renewable than we need. So you've got not a residual demand, but residual excess. And then question is, do we recharge our batteries and thermal storage, or do we export or import? And then again, we sort of use a battery and thermal storage device model to use this. How much power do we give to the battery or the thermal storage? How much do we lose in efficiencies? And then we balance it with the state of charge of that device. And finally, we sort of interchange with the grid and have any surplus curtailed or loss of supply included in that. So this is the model we sort of coded up, and then so this is a very simplified demand model. So we've got the blue line is the heat demand, and blue line is electricity demand, and the red on top is the added heat demand for the distillation process. So we're distilling 5 days a week, and otherwise we run ordinary 9-to-5 jobs and keep the shop open at the weekends too. Now, against this, I put in the renewable generation. The light and dark yellow are the PV power, and the green and the turquoise are the wind. And you see that sometimes there's the light yellow on top is what actually we don't have, and when it goes below, the shaded one is what we have managed to provide by renewables. And for instance, the green between the 6th and 8th of February is when we have no renewable generation, but still a minimum demand. So this visualizes sort of the mismatch between supply and demand. Right. If we now try to install a system which is only based on PV, we've got an average demand of 1 megawatt and peak demand of 3.6 megawatt, and the installed PV capacity start from 0 up to 10 megawatt peak. We know in the location we've got an overall annual capacity of 15%. You see that with increased PV capacity, we first increase the percentage of the consumption supplied locally. So at 2 megawatt peak, we supply about 20% of the local demand. But then this levels off at about 60%, so we never can meet all the demand by PV alone. So there's a point where the added benefit of spending more money on PV returns less benefit to the system. So curve flattens off noticeably, and an oversized PV system contributes little to local consumption, but then has us excess capacity which we might either need to export or dump. So absolute maximum is about 70%. If we now add storage to that PV only, we can push up the number of utilized electricity at the higher installed capacity. So for small PV, we don't need storage. For intermediate PV, we get some benefit from storage. For large PVs, we get clear benefit from storage, but again, that levels off. So for the 10 megawatt peak, we can bump up the supply from about 60 to maybe just under 80%, but even also that levels off at a certain storage capacity. So we can get good benefits up to about 10 megawatt hour storage capacity for the 10 megawatt peak PV, and after that we got more storage, but we don't actually get more benefit. If we do the same analysis for wind only, we see that the benefit of storage picks it much earlier, but also levels off at sort of the 80% bit, and the saturation of the benefit isn't quite as rapid as for the PV. So there's a slightly different profile, and of course that's all linked by the difference between PV being a strong seasonal and strong daily cycle, where the wind is much more irregular throughout the year. And we see that by matching a certain amount of PV and wind installation in the top right figure, we can sort of balance to an annual, fairly flat supply where we've got lots of sun in the summer when there's little wind and vice versa. So if you combine it, we can get the benefit of all three, but again, we get sort of a sweet point where we get the most benefit for least money investment. So just again, overview of the performance. Left column is small storage, right column is larger storage about 1 day's worth of operation on the right, half a day's worth of operation on the left. Top line is a small amount of installed capacity, bottom is larger amount. And we see that for the small storage on the left column, the benefit from installed generation capacity increases significantly from about half blue to about 2/3 per 80% blue. The storage capacity becomes smaller as we have got more generation, but still overall benefit is higher, and the red one is still what we cannot use from local generation. On the right side, with larger storage, the initial storage usage at the top right, the green bits on the top right, is much bigger than the left, so we can use the storage much more, so get much benefit. Bottom right compared to bottom left, the blues are the same because that's generation. The greens are the storage, very similar between left and right, and therefore not much difference in benefit from bigger storage. So quite a complicated picture, but the key message is storage can increase uptake to a limit. It's given by the nature of the resource and technologies, can be very effective to deal with daily cycle. So the size needs to cover the night and morning needs. And the benefit for wind requires larger storage than PV, but it covers more days rather than just a single day. Combining different types can also increase uptake of generation, and especially if you use different technologies which complement each other, like PV in summer and wind in winter. And optimum always appears to be a blend of several generation technologies and some storage. So that's me, and if you've got time, then we can have questions, and otherwise we go for the recordings and maybe have a question answer session at the end. So if I can ask for any hands up? No? And yes, we can do the poster 361 at the end if there's time. So do we have the recording for one of the papers? 271. If we can see the presentation, Valerie.
Good day.
Good day.
Today we tell about neural network control of green energy vehicles with blended braking systems. Some topics are touched in this presentation. We tell about, first, electrical vehicles. We are interested in energy management in these electrical vehicles in two modes, urgent braking and gradual braking. We tell about blended braking system, about neural networks, about simulation in MATLAB network tools, and about hardware in the loop experimentation. The problem arises between now the great volume of energy is lost mainly during braking. This is why it is interesting to find situations and tools when we can save as minimum part of this energy, and in this way to recover energy and to produce less emissions in this case. We studied different methods how to control energy recovery abilities. In this case, we were interested primarily in the blended braking system, which includes, to the left, friction braking, to the right, electrical braking. Of course, we are interested in braking with energy recovery. In this case, mainly the most important part is electrical braking. But in case of electrical braking, there are some limitations, and conventional controllers usually cannot overcome these limitations. This is why in this paper we stress on intelligent controllers. Intelligent controllers that provide gradual braking and urgent braking with anti-lock braking systems. So the topic is targeted to controllers and to method of control, especially in intelligent control, which is enough universal to provide different methods of control. The first system in this case is very simple. To the right upper part, we can say controller, braking system, and electrical vehicles. We set the required speed and control the real speed, find the required torque, and provide braking as we want. But in practice, it's impossible because electrical vehicle is strongly non-linear system. This is why the usual control, conventional control, CC, is not possible in real situations. This is why in a real situation, we need to stop braking, to continue braking, stop braking, continue braking, and our braking is interruptible in practice. To provide more sophisticated control, we usually use the circuit which is in the bottom of the slide to the right, intelligent controller, torque allocation system, which provide the allocation of torque between electrical braking and friction braking, blended braking system, which implements this control, and next, electrical vehicle and observer with command our controller. The system under the study looks like shown in this slide. Braking controller, which we developed during some years and presented during some presentations. Torque allocation system as a part of this braking controller. Driver, which selects the method how to control. For example, he decided, is it required urgent braking with anti-lock braking system, or maybe it is required gradual braking during the downhill driving, or maybe during parking, before lights, and so on. Our system selects between electrical braking and friction braking in the blended braking system, and electrical vehicle has the required number of sensors to send the signals to our braking controller. This is the system under the study. We compare two methods of control, conventional braking controllers. Here we developed some traditional controllers like PID controllers and threshold controllers, sliding mode controllers. We compared their possibilities and find some drawbacks of this method. This method, conventional, works enough nice when the situation is stable. On the road, the situation is not stable. The model of the system is non-linear. Deceleration may be very sharp in middle, and sometimes the deceleration is very smooth. Dead times appear, which are prohibited for the case of PID control and threshold control. And our system usually has multiple inputs and multiple outputs, which are not suitable for conventional controllers. This is why we come to the next stage, intelligent braking controllers. Among the intelligent braking controllers, we studied different approaches. In the previous conference here, I discussed fuzzy logic controllers. Today, we try to use for this purpose neural network controllers. Among the neural network controllers, we select different methods, and today we stress on model reference controllers. And there are different variants. For example, model reference control with PID, neuro-fuzzy controller, neuro-model reference controller, and so on. Different variants exist. This is a very suitable approach because now we can select between electrical braking and friction braking. We may find the situation when the friction braking used as reserve and electrical braking is as the main method. This is the great novelty of this approach. This is the system which we use in this study. Reference is our driver. The only his need is to press brake pedal or to release the gas pedal. That's all. He doesn't decide anything more. Our controller, now it is neural network controller, decides itself which method of control to select. It provides the reference torque, T star. The controller decides which brake select, torque allocator, electrical braking or friction braking. After that, these signals are going to our electrical vehicles, which have the possibility to get energy from the hybrid energy system and to send energy back to the same hybrid energy system. Hybrid energy system includes battery, maybe supercapacitors, maybe flywheels, and so on. It's not impossible. Our goal is to recover as much energy back as possible. In this situation, we can save energy and get less energy from outside. Different methods select how to control. Now we use so-called gradient control method. To this aim, we estimate the sleep of our motion. The problem exists in sleep because, of course, if you would like to stop as fast as possible, you would like to understand how great torque you may apply. Unlimited torque, it is impossible to apply because of sleep, and in this case, skidding appears. So we need to apply only the torque which is possible. To this aim, the goal is to understand the road under the tire. The road is unknown. It may be asphalt, it may be icy road, or wet road, different kind of roads. And our system does not know what road is under the tire. In this case, we don't know about the friction. And in this case, we don't know how great torque you may apply to avoid skidding. This is why that many traditional methods exist how to estimate the friction dependently on the slip. In our case, we try to replace friction with real torque under the tire and try to find the ratio between torque and slip, and to provide control using this ratio instead of a system which can understand the surface under the tire. This is when you approach, which we call gradient torque approach. The system has torque allocator. This torque allocator tries to understand how to apply this torque to our system. Our goal to apply fully electrical torque. It's impossible because of many limitations. State of charge, voltage limitation, current limitation, power limitation. So electrical system is very powerful, but it has much limitations as compared to traditional hydraulic friction. This is why our algorithm estimates all the sensors, and in the case of impossibility to use fully electrical braking, our system applies electrical plus friction or only friction as the final case. Using this torque allocator and this idea, we designed the model. The model was designed using the MATLAB Simulink, and here in this slide we can find different parts of this MATLAB Simulink model. For example, how to imitate electrical braking, how to use electrical machine in the mode of generation, electrical generation, or in the mode of electrical production. Different parts of these systems are shown in this slide. First, which was discussed in the previous conference, was fuzzy logic control. We invite some experts which provide us the possibility to control the system using the fuzzy logic approach. It was our first step. This step is enough popular among other designers from different companies, but it has enough many limitations, restrictions, and these restrictions are shown in these slides. So if you have experts, they may predict, of course, all the possibilities, but any time when the situation changes, again, you need to invite a new expert, and this expert must prepare the new fuzzy logic algorithm. It's enough unsuitable in the real situation when you produce the real electrical car. This is why today we use the neural network system. In this case, experts are not required. We require only learning the system in different situations. Our learning was provided using a number of 100 situations, different kind of roads, asphalt roads, rainy road, snowy road, icy road. We studied our system using different slopes of road, upslope, downslope. We have studied the system in different wind resistance. So many situations were studied in using these systems. As a result, we provide the model reference controller, which can collect this information. To design the controller, we use traditional approach, which is published in MATLAB literature. We replaces the physical model, real model, with physical model. After that, we replaced the physical model with neural network model of electrical vehicle, NEV, and we teach this system in many, many situations. After that, we try to study our controller, NNC, with this neural network system model and provide experimentations. Here, some results of these experimentations from the MATLAB are shown, and which to the left you can see different situations which are implemented using the control system very, very closely. And to the right, we can see some real possibilities when the driver press stop pedal and the system try to implement this result. Here you can find different models which were obtained. To the left, neural network model of electrical vehicle, and to the right, the neural network controller. After that, the model was ready, and we tried to experimentally evaluate our system. To this aim, we use a hardware in the loop stand from Germany, and using this stand with powerful drives, we imitated different situations from electric sport utility vehicles. And using this physical model, we provide experimentation with our neural network model prepared in MATLAB. Some results are shown in this slide. To the left, experimental result, to the right, theoretical result. They look enough similar, and this is our conclusion. The system can operate successfully in different situations. Here we demonstrate two situations. First, asphalt, next, icy road. Sometimes they change, and system must understand, yes, situation change. This is why the torque changes, the slip changes, and our control changes. So we cannot stop immediately in the case of ABS, anti-lock braking system, but we can stop as far as possible. And in all the cases, we use the full possibilities of electrical system. Maximum electrical torque is applied in all the situations. And only in the cases when this torque is not enough, only in this case, we apply additional friction brake. So here you can find our outputs. The new neural network system was developed. We compared this system experimentally and theoretical results, and they match one another enough successfully. And in this way, we demonstrate the ability to control electrical vehicle and to recover as much energy as possible in this control. Thank you.
Thank you very much. Any questions? Start with the audience. I think in look time, can we move on to paper 271?
Thank you.
I don't have that paper. How can I put it? I've got a written paper. And the key key message is looking at the difference in compressed air systems and liquefied air systems.
Our work called hybridization of non-manageable renewable energy here on behalf of our working group from University of Oviedo and the company Verdi to present our work called hybridization of non-manageable renewable energy plants with compressed or liquefied air storage. During my presentation, I will use the acronyms CAES or LAES for compressed energy storage systems or liquefied. Ladies and gentlemen, it is a pleasure for me to be here on behalf of our working group from University of Oviedo and the company Verdi to present our work called hybridization of non-manageable renewable energy plants with compressed or liquefied air storage. During my presentation, I will use the acronyms CAES or LAES for compressed air energy storage systems or liquefied air energy storage systems, and I will put an S at the beginning when we talk about small installations. The advancement of renewable energies must go hand in hand with the development of ways of storing energy that allow supply to be managed independently of the weather conditions, and in addition, security of supply and at competitive price must be guaranteed in a context of growing international competition for well resources. Optimizing generation through renewable sources involves ensuring that generators supply on a continuous basis all the energy capacity for which their facilities are designed, and that this supply is known in advance by the electrical system operator. It is not enough to substitute fossil fuel power capacity, but also energy availability. In addition to a reduction and correct allocation of emissions in the sector, a stabilization of the network, and a greater use of infrastructures that are designed for certain nominal operating parameters is achieved. To compensate for the variability of non-manageable renewable energies and to avoid jeopardizing the security of supply as well as maintaining the balance in the electrical system, manageable generation installations could be taken into account in the form of energy storage and international interconnection. This is why it is particularly necessary to develop energy storage that allow maximizing the use of electricity for renewable sources. Regarding technologies for fulfillment of instantaneous electricity demand, we have to say that it's necessary to provide autonomy from weather conditions to energy generating facilities from non-manageable renewable sources, so that they are capable of meeting the instantaneous demand. Wind energy is, together with hydroelectric, the most exergetic of renewable energies, but nevertheless, and in contrast to hydroelectric, it does not allow by itself to meet changing market demands. New ways of making the supply of wind energy manageable are being studied. One of the most promising technologies currently under study and already in an initial demonstration phase is obtaining hydrogen by electrolysis of water from wind electricity. Obtaining hydrogen will mean the availability of a fuel that can be stored to meet the demand for electricity deferred from the time it's produced. The use of hydrogen as a fuel will require that the wind power installation have a support thermal power plant or a fuel cell. In this way, the market demand for electricity can be met, either through that obtained directly from wind turbines or through that obtained from the fuel cell installation or the combustion of hydrogen to drive a steam turbine, a gas turbine, or an internal combustion engine. The chemical process will only take part when the wind turbines require support to provide 100% of the installed power. It's important to underline the advantage that means the hygroscopic cycle technology in the support of renewable energy facilities, since a thermal power plant can be built wherever it's needed, with no limitation due to ambient conditions or water availability. This technology allows steam to be condensed in dry mode facilities independently of the ambient air temperature. We have experienced in real condition in Córdoba, Spain, at 40 Celsius degrees ambient air temperature. The efficiency of the thermal plant is increased by taking the steam turbine to the lowest vacuum it can reach. There are other open ways of research whose objective is also to make the supply of electrical energy produced by wind turbines manageable. In areas with suitable orography, surplus wind is used to lift water and thus store potential energy. This system needs to have a vast and suitable land for water storage facility of this type. We will go through compressed air energy storage technologies. The diathermic technology is the one used by the oldest compressed air storage power plants currently operating. In this case, the compressed air is used as a comburent in a gas turbine. Regarding adiabatic technology, this technology does not feature heat exchangers at the compressor outlet, since the storage is done at compressed air pressure and temperature. Subsequently, the air is released at an expansion turbine coupled to an electric generator, nor does it need of the combustion unit of diathermic plants. The lower number of components compared to diathermic technology reduces thermal losses, but however it requires a good insulation system and sealing to be able to maintain the energy of the compressed air. These systems are currently in the research and development phase. Regarding isothermal type case systems, are still in the early research and development stage, prior to a demonstration installation. According to its promoters, instead of compressing and expanding the air in turbochargers and turbines, where the process is intrinsically adiabatic, the isothermal system compresses and expands the gas inside hydraulic cylinders, which allows a controlled heat transfer with the environment as a reservoir during compression and expansion. Thermal performance above 90% are expected for both compression and expansion. We have obtained the parameters for more efficient wind and skies hybrid plant. Considered options for calculations are a diathermic sky cycle with thermal recovery and an adiabatic sky cycle with pneumatic motor. Results are later extrapolated to an adiabatic sky cycle with expansion turbine that at the moment is being developed as a modification of a steam turbine. From the studied alternatives, the most advantageous is the adiabatic since it's more efficient, it's simpler, and it does not require a gas turbine or the installation of the fuel for the latter. It has a lower investment and O&M cost and can operate exclusively with renewable energy. This is why only adiabatic option results are shown. The studied system has two problems. The first lies in the storage medium and conduction pipes, which must be built to support high pressure and temperature conditions. The second problem lies in the lack of equipment suitable for operating in definite working conditions. Motors for those pressures and temperatures are not available. The study has been remade considering an expansion turbine. Found the problems of SKY's system, we have studied the liquefied air energy storage. Main limitation of energy storage as compressed air is the large volume needed to store an enough mass of air. Instead of storing air in the gaseous phase, much higher energy density can be reached by storing air in the liquid phase. In a gas system, stored energy density available is about 18 megajoules per cubic meter. The energy per unit volume of liquefied air is 660 megajoules per cubic meter. Therefore, there is great potential for more compact energy storage. For studying the liquefied air energy storage, we have taken this scheme from high-view power storage. In this case, the air collected from the environment is compressed and filtered. Water and carbon dioxide are removed so that they do not freeze and block the liquefaction process. Compressed air is cooled and expanded in successive stages so that, in the most part, it's liquefied. This liquefied air is stored in a thermally insulated tank. When it's convenient to generate electricity for its discharge into the grid, liquefied air is heated by exchanging heat with a fluid with higher temperature, ambient air for example, and it is expanded in a turbine system. The air expansion in the turbines follows a Rankine cycle. The generation of electricity from stored liquefied air requires the use of the same components that have been considered during the study of the SKY's technologies available for this purpose. Main difference is the chosen storage system. As conclusions, we can say that the economic SKY's viability of the facility is determined by the following factors. The cost of storage must be lower than 4 euros per stored kilowatt. This value is much lower than current air storage cost. Compressed calculated storage that makes the facility economically viable is about 40 cubic meters per megawatt hour. The ratio of consumption time for storage versus generation time that makes the installation to be economically viable is 1:3. In the case of SLICE, calculated storage rate that makes the facility economically viable is approximately 0.07 cubic meter per megawatt hour, and the ratio of consumption time in storage versus generation time that makes the installation economically viable is 1/3. Energy storage in the form of liquefied air is, for small power generation facilities, more viable economically than energy storage in the form of compressed air. The independence of facility equipped with sky or slice storage system from external fuels represents an important strategic value from the point of view of supply assurance. Finishing the presentation, I take you an example of the presentation. Please do not hesitate to contact me by mail, and I will try to answer any question you can make. Thank you very much, and we keep in touch.
Right, that was, thank you very much. That was a very nice presentation. Now we move to the role of honeycomb structure in improving the melting process of phase change material inside a latent heat storage unit by Harris, Al-Alami, and Uni. And again, this is a recording that you can start it now.
We start with the plan of this presentation, which is detailed as follows. First of all, I will present a quick introduction on the subjects and discuss the main problem of this work. Second, with the plan of this presentation with Manal, PhD student in the physics of materials, microelectronics, automations, and thermal laboratory. Today, I will present to you part of my thesis work entitled Role of Honeycomb Structure in Improving the Melting Process of a Phase Change Material Inside a Latent Heat Storage Unit. So we start with the plan of this presentation, which is detailed as follows. First of all, I will present a quick introduction on the subjects and discuss the main problem of this work. Secondly, I will represent the validation study. After that, I will expose the system and method of calculation proposed in this numerical study. The fourth part will be devoted to the results. And lastly, I will focus on conclusions and perspectives. The storage of thermal energy is considered to be an efficient solution for renewable applications. Generally, thermal energy storage can be achieved in three forms, namely sensitive, latent, and thermochemical. Among these, the latent thermal energy storage system has proven to be the most efficient. From the point of view of higher storage density and storage of thermal energy at a constant temperature. However, the main drawback of latent heat thermal energy storage system is the low thermal conductivity of current PTM. This weakens thermal conductions in these systems, resulting in considerably long energy storage and recovery times. To increase the thermal conductivity of PTM, different studies examine different approaches, including the expansion of the heat transfer zone using thin metal matrix, carbon nanotube, and the use of nanoparticles. To ensure the accuracy of the current numerical approach, the average liquid fraction is verified with the experimental results of Sukahman and Kamkawi. The lauric acid is filled into a rectangular enclosure with an inside dimensions of 120 mm in height and 50 mm in width and depth. The right wall of the cavity is subjected to a constant temperature, while adiabatic boundary conditions are set on the other walls. From this figure, it can be seen that the numerical model is very consistent with the experimental results. To remedy this problem, we carry out a numerical study based on the numerical simulation of the fusion of a phase-change material within a rectangular enclosure with a metal matrix, using the ANSYS Fluent software. This study is motivated by the need to better understand the heat transfer during the charging phase of the thermal energy storage system. In addition, we have proposed in parallel a comparative study between the two configurations. We are talking about a rectangular enclosure without and with honeycombs. Both configurations are subjected to the same boundary condition. The bottom wall is subjected to a constant flux density. We impose natural convection on the upper wall, and we assume that vertical walls are isolated. In order to simplify the calculation, a transient two-dimensional model of heat transfer during the PCM melting process was governed by the following general assumptions. First of all, we see that thermophysical properties of PCM are constant. Secondly, the fluid is assimilated to a Newtonian and incompressible fluid, and we neglect convection in the liquid phase due to the great value of the PCM viscosity. We now move on the discussion of the results. The following image represents the evolution of the phase change interface for the two configurations, i.e. configuration with and without honeycomb. First of all, I would like to point out that the colors blue and red represent the condition when the material is completely solid and liquid respectively. We can observe that at this start time between 0 and 500 seconds of the fusion process, the fusion interface starts from bottom to top, near the source. This indicates that in the early stages, heat transfer occurs mainly by conduction. We also note that the evolution of fusion begins with the edges of the core of a honeycomb and propagates towards the middle of the hexagon. After 3000 seconds, all of the PCM was melted, giving a melting fraction of close to 100% for the first configuration, with metal matrix. However, the fraction was still not completed in the second case. The liquid fraction is a typical dimensionless parameter that characterizes the charging characteristics of latent heat storage unit. This figure depicts the variation of liquid fraction for icosane in a rectangular enclosure, with and without honeycomb structure during the melting process. In the early stage, we note that the evolution of liquid fraction is similar and linear for both configurations, and the heat transfer is mainly by conduction. We also note that the increase in the rate of liquid fraction for the latent heat storage unit with the metallic matrix is faster than the unit with the pure PCM. Furthermore, the impregnation of the honeycomb structure makes it possible to reduce the complete melting time by 30%. According to the numerical analysis carried out using ANSYS Fluent, we conclude that the addition of metal matrix allows to increasing and improving the performance of the system. At the moment, we are comparing the use of a metal matrix with other heat transfer enhancement methods. And we also intend to study the effects of tilt angle on the system performance. Thank you for your attention.
And I believe contribution 287 on the heat things to batteries through unmanned air vehicles is not there. So we can actually now this time give time to the posters against 61 who didn't have the chance in the last session. So Oscar, if you're still around, take the floor for your poster. Oscar, I hear you there, I see you there. Do share your presentation and unmute yourself to give us your poster. So why is getting ready? So that poster was about wind energy system in Ambocas, Ecuador, looking at distributed generation and energy quality. And last chance for Oscar. Otherwise, look at poster 361 from the website, and he's got his contact details there. So, Oscar, 1, 2, 3, gone. So let's conclude the session. Thank you to those who were in the hall. Thank you to those online, and all the support who made it possible. That we can look forward to the full session. Thank you very much.
So we close the session.